Okay, grade 11, here we are with lesson number 8. It's talking about Pearson's correlation and the t-test, two possible different statistical tests you may want to use, and either of them could show up on your assessment. We do a two-test assessment, actually multiple statistical, both of them could show up. So first thing, let's talk about significance and what significance means. Because the whole point of doing these tests is to see if the relationship is statistically significant or not. So what does that actually mean? Well, have you ever heard the phrase, this is statistically significant? Probably, right? And what it means is it means we have to be certain enough that the relationship between the two variables is not caused by chance. The pattern is actually unlikely to happen due to chance. It has to be caused by the variables interacting. So if we want to see if the difference between two data sets is due to chance alone or due to variability in the population of a sample alone, or whether that is due to some sort of relationship between the variables. So the independent variable is causing this change in the dependent variables or not. So to do this, we have to figure out, is it statistically significant? And there's a bunch of tests you can do to do this, and the test you choose really depends on the data you have. What the data you have available to you, how much data you have, what direction you look at it in, that kind of stuff. So we're going to learn a bunch of different tests to do this, and today we're going to talk about the t-test and Pearson's correlation coefficient as ways to do this. If your data is not statistically significant, then there is no relationship between the variables. Okay, we can't say that there's no relationship. It could just be that any semblance of a pattern is just due to chance alone. Okay, so if you look at this little cartoon here, the p-value is a value that'll tell us if we're significant or not, and if it's just below 0.05, then your data is not considered significant. Okay, so this is actually a common problem, let's say a problem, but a phenomenon in research where people do a ton of research, collect tons of data, thinking they've found a relationship, and then they run their stats and they get a p-value that's too high, it's too low, and it means there is no real relationship there. And it's important to understand when there is no relationship as well. It's also a very valid conclusion. So don't think you can only do a good job if you find a significant relationship. Finding no relationship is also telling us something. But a lot of people kind of have they want to find a relationship to prove there's something there. So probability. What does the word probability mean? Well, hopefully it should be the likelihood of something happening, right? And for probability we use in statistics is a little bit different. It's a probability value that is set by different fields, and we call it the p-value. Okay, so you have to talk about when you're doing your test what p-value you used, so that people know just how certain you are about the relationship between your variables. And the p-value is the probability that chance alone could produce the difference you're seeing. So how big of a percentage are you willing to give it to that chance alone could have caused this difference? So if it is 0.05, what does the p-value mean? Well, that means that you're accepting just that 5% chance that the relationship to your variables is caused by chance alone, which means you are 95% certain that that difference is not caused by chance alone. Now, 0.05 is the accepted p-value in science, so that's a value you're using for your research as well. So if you get a value from your tests, it's less than 0.05, then it is statistically significant. The lower it is, the better. If it's at 0.01, that means you are 99% certain the relationship between your variables is caused by a relationship and not by chance alone. So if I look at this bell curve here, my normal curve, the p-value is often split between both extremes. And so the observed data fits into this area, and you are 95% the relationship is in this part here, and you have 2.5% here, 2.5% here. If you're using 0.01 for your p-value, which would be 0.005 here, 0.005 here. Okay, so it's 1%, 0.5% on each extreme here. Okay, so another way to look at this is if you have a p-value of less than 0.05, that means the likelihood of observing the data occurring if the null hypothesis is correct. Okay, remember we talked about null hypothesis earlier, but null hypothesis being there is no relationship. Okay, if the experimental hypothesis is correct, what is that p-value? It's going to be 95%, right? So if p-value is less than 0.05, that's what we're going to use in science. That means there's a 95% probability that the answer, the relationship you're finding, is due to relationship and not chance, not just normal variation in that particular sample set. Okay, let's look at our first test, which would be Pearson's correlation. Now, you don't have to memorize how to do these, but you have to take really good notes and write the formulas and everything down so you can do them yourselves for both your mock IA, your real IA, and your assignment, and your final exam. This could show up on any of those things. So make sure you have all the information you need really well described. And do the practice questions, okay? It's not something you want to be doing for the first time from scratch on a summative. That would be a very, very foolish thing to do. Okay, so one of the most common tasks is a pretty simple test to do, is used to quantify correlation. So this only happens, you only use this test if you have variables that already demonstrate a correlation, and it just gives you a way to quantify that correlation. How strong is that correlation? And so that's a little R value. So when we talk about R squared is regression, that's not the same thing as Pearson's correlation. They're both R, but they have different meanings. Okay, so R squared is regression. The R value is an actual statistical test. And the range of R values can go from -1 up to +1. So negative values are a negative correlation and positive values are a positive correlation, which makes sense. So here I have my positive ones. My R value is 0.3, 0.7. My negative one it's negative 0.7, so negative correlations, and my R value is 0. It's no correlation at all in the data. So the answer, R value of 0, which is no correlation, no relationship, no correlation to those two variables. Okay, so if you have an R value that's exactly equal to 1, then for every increase in the X value, then the Y value is going to also increase in the exact proportion. So if you think of a good example of that, a positive relationship here would be shoe size and foot length. So every increase in foot length should equal to an equal increase in shoe size. Here's a formula for Pearson's correlation. We will do a practice question with this, but make sure you have this written down very clearly in your notes, because I will not be providing it to you for your assessment or anything. You have to have your own notes that are really clearly written out. You may want to make a formula sheet that just has all the formulas on it. Okay. Yeah, just a second. Yeah, okay. So if you have an R value of -1, that means for every increase in the X value, then the Y value will decrease. So negative is a negative relationship, negative correlation is 1 is increasing, 1 is decreasing, but it's in an exact proportion if the R value is -1. So for example, if the gas tank level and speed, you increase your speed, your gas tank level should decrease in equal proportion to how fast you're going. Now this is a quantitative value. The absolute value, the final calculation value, tells you how strong that correlation is. So of course an R value of 0.75 is a stronger correlation than an R value of 0.65. And that's a useful thing to have, to know, is comparing different R values for different data sets. Now the full way we look at this, and be careful because there are a lot of different correlation coefficients. So the Pearson's correlation coefficient, the official name is a Pearson's product moment correlation. Okay, and it works only for linear relationships between two variables. Now, this is not a good test to choose in some ways, depending on your data set and what you're looking for, because it can't differentiate between the dependent and independent variables. So for this example data set here, we have age and cholesterol level. If you picked this is X and this is Y, or this is Y and this is X, either way, it would show the relationship. So it could show that cholesterol increases with age, and it could also show that age increases with cholesterol. So be careful with that, because it can sometimes imply causation or correlation that's not really there, which means this might not be the best test depending on what your data you're looking for. But it's a decent test. Okay, so to calculate by hand, what you have to look at the formula here is you have to do the sum of the difference between the individual X value and the mean X value. multiply the difference between each individual y value and the mean y value. Values. And then divide by the square root of the sum of the squares. So let's try it here. What I do is I make a data set like this, make a table. So I have my original data table here, and then I'm going to do these values here. So using this formula here, okay? So I have my first row, subject number 1, age is 18, cholesterol is 5.4. This is my x value, that's my y. So my x times y, these two gives me 97.2, x squared, 324, y squared, 29.16. And I do that for every row of the table. And I had 10, this is my original table. I just added these columns on the right with my x times y, my x squared, and my y squared values. And then, because of my formula, I have all these sums. Sigma means sums. I have to do the sum. So sum of the ages is 211. Sum of cholesterol, 78.4. Sum of x times y, 1705.7. X squared sum, 4,515. And y squared sum, 668.18. And I plug these numbers into my formula. I often find with doing stool tests, if you keep your data into table form, it just makes it easier not to lose bits of it and keeping it clear. So you'll see to have n, and n is a number of subjects. In this case, that would be 10. So let's give it a try. Here's the formula, here's your numbers. Pause the video, try it, calculate it yourself. Okay, so if you tried it and you're a little bit stuck, here is the first level substitution. So I'm replacing my n by 10. My sum of x times y is this value, 1705.7 here, minus the sum of x, the sum of y, minus 211, sum of x, minus times 78.4, the sum of y, over the square root of n, which is 10, times the sum of x squared. So here's my sum of x squared. 4,515 minus the sum of x, 211 squared. And same thing here with my y values. 10 is my n times the sum of y squared, 668.18, minus the sum of y squared. Okay, so if you didn't quite get it yet, pause and try to finish that off. Use your order of operations. Okay, so you should have gotten this value, 0.887. Did you get it right? If you didn't, go back and figure out where you went wrong. Okay, so now we have that value. We have our value, but is our R value actually significant or not? So to do this, we have to have a few different pieces of information, and we have to have a Pearson's coefficient critical values chart. So here's a sample of this. You can Google them. You can use ones I give you, but they're readily available values charts. To do this, you figure the confidence level. So we're going to use 0.05. Okay, it's our p-value, or sometimes called alpha in this case. This is our column we're going to use. If you would be even more precise, you use a 0.01, which means you're 99% certain. This means 95% certain. We also need the degrees of freedom, or in this case, just giving us n, and our n value is 10, of course. So sometimes you'll see it says df, that's degrees of freedom. And degrees of freedom for this particular test is n minus 2. So in this case, that would be 10 minus 2 is 8. Okay, so our R value is plus 0.887. So what does that mean? Well, we're looking at this row here. We had n, we had 10 individuals in our subject sample. We are using this alpha value, this p-value at 0.05. So 0.632 is our critical value. So that means because our number is smaller than that our correlation is significant. Yay! There is a significant positive relationship between age and cholesterol level with R8. So we put the degrees of freedom here. R value, degrees of freedom 8 equals plus 0.887, where P is less than 0.05. This is how you would report that in a conclusion or in your part of your analysis of your lab. You say what you did and what it means. Okay, our second test is the t-test. So this is a student's t-test, and this is actually submitted by a guy who worked for the Guinness Brewery in Dublin. And the reason why it's called student's t-test is because he wanted to publish it, this new test he had designed to compare, I believe it was barley populations, samples, and how something about the parameters of the barley. And because Guinness was very secretive about their brewery and how they grew their barley and all that kind of stuff for their beer, they wouldn't let him publish it. But eventually he was really important to publish it, so he had to put a pseudonym, and he chose the name Student. So now we still call it Student's T-Test this day. A little bit of statistics trivia for you there, guys. So we're going to compare two populations, and these populations are assumed to have an equal variance and are unrelated. Okay, so they have equal kind of variability, and they're unrelated to each other. And it's an independent samples t-test. And we're going to use several different steps. The formula we have here, the t-test formula, you should write down, it's just the first step, and that allows you to figure out what the t-value is going to be. And then like with the correlation, Pearson's correlation, you have to compare that to a critical values table to figure out if it's significant or not. So this is when you can use a t-test if the data is not paired. If the two variables have independent normal distributions, so they're both showing a normal distribution in the data set. If the two variables have the same known variance or unknown variance. And it works better with samples of at least 30 data points, where my 30 has been coming from all along. But you can use it for smaller data points if you're less likely to have a significant relationship. Okay, so before we can do the test, let's talk about our null hypothesis. We already talked about this a little bit, but I want to come back to it. So we consider the null hypothesis for any single test, including Pearson's, but I wanted to do one test before I talk about this to kind of give you some context. So null, as we already talked about, means there's nothing. It's nothing is there. So the null hypothesis, or H naught, states there is no statistically significant difference between the samples. So for this fish experiment, we looked at this one already before, how the density of the fish population affects the mean length of the fish. The null hypothesis would be there is no difference in mean length between the denser and less dense populations. So here's my data set. I have an aquarium with 10 fish, and here's the mean length of those fish, of some of those 10 fish. Here's an aquarium that has 40 fish, and I don't have all 40 fish written down. I'm just going with 20. That's enough for my sample. So first thing, the mean for each population, the mean fish length here is 52.8. The mean fish length here is 53.7. So pretty similar means. Is there a relationship here, a difference between the two? Well, here's my formula. Here's my data table again. I figured the standard deviation. You guys know how to do it by hand by now, but if you don't want to do it by hand because it's a pain in the butt, you can also use a calculator, either Excel, Google Sheets. You can also just Google standard deviation calculator, and it will do it for you to plug all the data in. Okay, and so I'm giving it to you here, so you can, instead of having to do it yourself to find a calculator, but on your exam, something you'll need to make sure you can do standard deviation on your assignment. Okay, so here is my first bit of formula. I've set my values in. Pause the video, try and finish it off yourself. Okay, so if you finish off your numbers and you got 0.357, notice we don't keep a negative sign here. There's no negative value. So 0.357 is my t-value for this fish population question, the fish length question. Did you get that? If you didn't, go back and try and figure out what went wrong. Now, is that significant? So I have a different table here because every test has a different critical values table. So we have to look at the information and this two-tailed chart. So we're doing a two-tailed chart because two-tailed means in both a negative and positive directions, and we're not sure which direction this relationship might be different. So we're going to use, of course, our 0.05 confidence level. That's acceptable in science. And because we're doing two tails, we're going to be using this column. Two tails, 0.05. I would always use two tails. You only use one tail if you're really certain it's only going to vary in one direction. Like you're always sure it's going to vary above versus below, but it's really hard to know that, so I would not go with a one-tail test ever until you take a lot more stats. We also know the degrees of freedom. So for the degrees of freedom for this test, for the t-test, you do n1 plus N2 minus 2. So doing a two-tailed test, do minus 2. So what's our degrees of freedom in our fish sample? Well, N1 was 10, N2 was 20, so that's 30 minus 2. Our degrees of freedom is 28. So here's our table. We're going to go down this column here, find degrees of freedom of 28 right here. We're going to follow this row all the way across to our 0.05 value for two tails, which is actually right here, here, and here. That's what we want to look at. So here I kind of zoomed in that part. 28, 0.05, our degrees of freedom was 28, our p-value is 0.05, and our t-value was 0.357 that we calculated. So do we accept or reject the null? Well, our t-value is below our critical value, which is 2.048, not 2.00. Typo. Since it's below, so the critical value is above and our calculated value is below, we do not reject the null, which means there is no difference between mean fish length, between the more and less dense fish populations. Now, if I had did this maybe with more data, I might have seen different response. So part of why it's so important to have significant and enough data to get a clear response. Maybe if I had more samples, maybe I had like 40, did all 40 fish from the second tank and then just doing 20 of them, maybe I would have had a different answer. Okay, so that's the end of our two different tests for today. Where you're actually with your mock IA is keep working on it, of course. Your topic should be approved if you're finishing up your methods, if you haven't already, and getting started collecting your data. If you haven't articulated your data, you need to get on this because it's going to be due in 2 weeks. Okay? Feel free to email me anytime and I'll get back to you and we can talk about your IA. So homework is uploading your notes, including your practice calculations, which you have to do by hand. I want to see you guys doing this by hand at least one time because you'll have to do that for your assignment and you need support in your practice. Next week you have your assignment, for which you will use your notes, which you have very thorough notes to do so, and keep working on your mock IA. You're all at different points in that, and I'll be checking with you individually next week. Alright guys, hope this is helpful for you. There's lots of other YouTube videos and stuff on both t-test and Pearson's correlation you're welcome to look at to help you. You should take really thorough notes. You're going to need your notes for the mock IA, for the real IA, for the test, for the assignment, for the final exam, all that stuff. Alright, take care and stay safe.